Hello, welcome to Program with Sam, and this is R Lesson 5. So today we're going to be looking at writing some functions in R, or like one or two functions. And the goal is being to create a function that can perform a mathematical equation. For example, we could make a function that defines f of x, and it will take an input and return some output. And this is obviously then usable for graphing. So let's go ahead and start by writing a function. Now, making functions in R is kind of similar to Python when we were looking at functional programming and you assign the function to almost a variable, so to speak. So if we say that we have our function f and we want it to be a function, we say that and we give it the argument. So we're going to say it's a function of x. We open our curly braces, and then on the inside all we want to do is y is equal to say 2 times x and minus 4 or something like that. And then if we run that, it will compile a function. And you can see I already tested that worked okay. And yeah, it does. Spoilers. So with that in mind, I've generated some dummy values up there that we can then prove that it works. So what we can do is plot, and we can set x is equal to those values and y is equal to the function applied to those values. And then the type will be just the line. And if we give that a run, it'll generate our line graph just like that. And that's essentially the equation. We could change it by doing like to the power and stuff, or you could change the lines even more. We could make it more steep by doing it like that. And so on and so forth. Although it looks like it's staying the same and just changing the scale on there every single time. So if we do 12, the gradient remains the same on the graph, but the scales of the axes have changed, and that's why. Which is interesting and something you should definitely bear in mind when it comes to plotting your functions. Another thing that it's possible to do is to use R to solve systems of differential equations. And this is, for example, predator-prey scenario, where you have the population varying with the population of another species, and they're sort of like codependent, co-linked. And you can use R to actually write code that then solves that differential system. So I actually have some code here that I use for my coursework, and we did something very, very similar. You're going to need a library called dsolve. So if you put that in there and run, you might have to download it, which you know how to do because we looked at that in the first episode. And let's do this. We'll take this equation system. So you have dx is equal to x times, and then it's a function of by, of y, and then you have dy is a function of y and x. So obviously you can't necessarily solve it in the algebraic sense. You need to solve it in a different manner. So this is what R is going to do. Given a set of sort of initial parameters, we can use the ODE function to essentially calculate and solve the differential system. Now, with that in mind, we can then plot the differential system. So if I then select all of that and run it, it's then plotting the differential system here of the dx with respect to dy. And that is those are the two lines that are produced as a result. So I believe this is population of fish and this is population of humans over time. And that's the resulting graph. So what we've done is we've essentially created a function that takes multiple arguments and then uses it to solve the two functions and returns the results in the form of a list. Now, it will do that for all of the parameters that you put in. So when you put these in, for every parameter, it's going to solve all of them and then return as a list the results, which are then plotted on the graph. And that is then helped by this ODE function, which is an ordinary differential equation solver in R, and it just takes our equation system as the function. then it just plots it out using matplot. And this can then be used for a multitude of other things. Like, for example, we can use the same principle to solve higher order differential equations. And we can also use it to actually plot predator-prey spiral graphs as well. There's a plethora of things that you can do with this. So since R is a language that primarily utilizes vectors and matrices for storing the data, it makes sense that you'd be able to do things like singular value decomposition as well as calculating covariance. So I've set up a little matrix here, and I believe we've touched on this before in the series, but one thing we can do is we can say the covmat is equal to cov and then pass it mat. And if we do that and output the covariance matrix, you can see that we've calculated the covariance matrix of the given matrix. And it's possible to actually do singular value decomposition of the matrix. So if we do SVD results and we pass it SVD and matrix, and then we just print out the results, I believe this should work. And it prints out the single value decomposition of the matrix. And there's other functions that you can do with matrices as well. And obviously we've looked at apply and lapply and all the different sorts of functions that can be used on matrices in previous episodes. But it's just worth reminding you that those functions are out there, especially since like R is a mathematics language. It was developed for mathematicians realistically. So it makes a lot of sense that all of the focus is on mathematics and solving mathematical problems. It's one of the reasons why it indexes at 1 and not 0, is because in programming and computer science, we tend to index things from 0. Mathematicians tend to not like that very much. And as a result, R was developed with more of a maths focus. And whilst it is a powerful language in some respects, it does behave very differently to any programming language that you'll have used before. And that is it for this one. Next time, well, there is no next time. That's it for R as well. Thank you very much for watching, and I hope you found this informative, and I'll see you in the next series. Bye.